All right, I think we're streaming live. And so what I would like to do is maybe start. Oh, this is kind of crazy. I'm going to start with the screen share. Oh, what's this? ERT labs are not ideal. To be honest, I think the coding is probably better than any labs we've had to do, just because whether you like it or not, coding actually is going to help you get a job someday. It's something you can put on your resume. And even if you don't, yeah, so that matters more than those nonsense video labs, right? But they served their purpose. They did what they needed to do, but you really learn a job skill with the coding. That said, why don't we start with a screen share? And we're trying to learn about chapter 13. And I think this may show you one of the reasons coding can actually be useful. We're going to learn about gravitational forces here. And maybe what I'll do is I'll write the gravitational force equation right here. There's an equation, the force due to, let's say, of 1 on 2. And if you're in your workbook, let me give you a workbook page. Where is my workbook? We're on chapter 13, which is page. Give me a sec. Sorry about that. 117. So if you want to have your workbook open to page 117, that would be a good thing to go with this. All right. And now this equation is not going to make a lot of sense until hopefully it will make more sense when I show you the simulation. And this will give you a foreshadowing of what we do in lab this week. So I'm just writing the equation straight from page 117. And I made a mistake. That's a hat. Okay, so this is the equation that we're going to want to model here. You know, the chemists, it's got to be hard on the chemists teaching right now. I know I make fun of a lot of chemists, but man, they've got it tough. It is not easy for them to teach online. And just, yeah, anybody that's teaching lab right now knows that it's, anybody taking a lab, we all know. I feel sorry for them. All right. And that's me, a physicist. Woo, it's bad. They're hard. It's just not ideal. All right. So let's focus on what we've got to do right now. So take a look here. This is just a coordinate system. You know what that is. This is a constant. Big G is this value right here. This big G that I'm circling right here. That is 6.67 times 10 to the minus 11th. Maybe you could tell by looking at it what the units are. Can anybody tell me what the units of big G must be by looking at it? Look at this equation right here. Force is going to be in newtons. What are the units of big G?
Newtons times kilogram squared divided by meter squared.
I think you got them.
Or meter squared, yeah.
Yep, because you're going to have to cross multiply by the meter squared, and then the kilogram squared come up on the bottom.
Right.
Does everybody kind of see that? Like I have to divide by the meter, or oh shoot, I just said it too. I have to divide by the kilograms, which is letter M, and multiply by 2 of those. Now I'm going to get rid of those dots just so I don't have a bunch of umlauts sitting around. All right. So in this case, and let me erase this. So that's the units of this constant. Now look at what this code does. I could specify the 2 locations of these rocks. Let's say these are rocks deep in space. Now, the vector from 1 to 2, this is the initial and this is the final. So notice the equation is final position minus initial position. So initial is 1, final is 2. That's why 2 comes first in this equation. Now, here is this calculation. At first, it doesn't look the same. Look carefully at this. I have my constant, G. I have the mass. I have the other mass. And then look at this. This is a vector, and this is the magnitude cubed. Well, I just want to point out something. R hat is by definition, the vector divided by the magnitude. As a result, if I look at this r hat right there, I hope you agree that when I plug this junk into that, I'd get an r cubed on the bottom, and I'd get a vector instead of a hat. So that's what this equation does. So this upper definition is the one you always see in textbooks, and it's a great definition. In a practical world, this is how you end up coding it or computing it in both Physics 161 and Physics 163. Okay. So I'm just going to pause. Is everybody okay with why I'm able to do the r hat versus the r vector? Any questions about that?
I understand how you do it, but why couldn't you just use r hat?
You could.
Okay.
So you could do it like, oh, whoops. Hold on. I think I can hit undo. So let me hit this. Let me get, that's what I wanted. Let me get this out of here and this out of here. And just let me do this. You could also do it this way, Esteban. Is that big enough to be seen? Hopefully you guys, can you actually read the text on my screen?
Yeah.
Okay. I could do this. Negative hat of that. I'll just put in some space so you can see it. I don't know if this is good etiquette. And then I could put in a squared. Those should be exactly the same computation. Got it?
Right.
Why do you think I chose line 27?
I have no idea. That's what I'm trying to figure out.
It's shorter.
It's shorter. Oh, okay.
You call one less function.
Okay.
So imagine if you're running this and your computer starts slowing down because you have to do this a bunch of times. This upper one uses one less function call. It's more efficient. And so it literally I don't know if it doubles the computation speed, but it certainly increases the computation speed. So if this has to be calculated inside a loop, the upper one is definitely advantageous. You still have to call the magnitude anyways and still have to raise it to a power, but you don't have to call the hat function.
Yeah. Okay.
It's just for computational efficiency, not because it's better. That's it. I guess not because it's yeah. All right. Is that good enough?
Yeah.
All right. So then notice this little bit of code here. This is going to seem a little silly at first, but what I'm going to do is I'm going to specify a saturation level. And the idea here is if the size of my arrow gets too big, I'm going to limit it to the saturation level, right? So notice, again, I'm just worried about drawing the arrows here, not actually doing anything else. But basically, if the arrow is going to be too large, I limit it to the sat level, but then I draw it in the direction of the original force. So this little bit of code here just says, hey, let's reduce the maximum possible size of any arrows to 10. This is very different than scaling all arrows by an equal quantity. This is setting an upper limit. All right. Why do we need to do that? Why is this force going to sometimes blow up? Does anybody see it in the equation here in line 27 or on the right side of my screen? Why do we have to worry about these forces getting enormous?
They get like super close to each other because it's by like a square. It then just get.
Yeah, if the two objects get close together, this goes towards zero, and you could get an enormous force output. So that's kind of the issue that we have to do this for. Now, all right, let's go ahead and run this program. So I've got all that stuff over there. So I'm just going to kind of zoom in on this one particular case. The idea is if I pick 2 points, the gravitational force between them points directly from one ball towards the other ball. Got it? Now, let's do some simple cases here. Let's make this radius a little bit smaller, just so it's not as obtrusive. And let's do some simple cases. Let's say 3. Actually, let's do 2s. Okay, so let's say -2 and 2. So let's think. Do you think the force is going to get bigger or smaller? The other numbers were like 4 and 3. What's your gut tell you? Will the force get bigger or smaller?
Smaller,
Should be bigger
bigger.
because they're
Us-
closer together.
Right. Oh, okay, I got it backwards.
Yeah, so the r vector is smaller, and because it's 1 over that magnitude, it could be a larger force. So just to show you this, let's say I double the distance. So right now, what is the distance between these 2 point masses?
2
4.
or 4.
Right? So if I double the distance and make them 8 units apart, what should happen to the size of the force?
So it should be cut in half.
Ah, really? So what is it? Take a guess. You're wrong. So it was 66.
Drop by a factor of 4.
4 because it's r squared.
Yeah, inverse squared.
See that? So it got divided by, right. So it used to be about 64. Now it's about 16.
Makes sense.
Got
I
it?
just didn't think it through, but yeah.
Yep.
Okay.
And so these are the little things that are going to help you check your work. So that's why I'm going through them now before you get too far ahead of yourself. So far, so good. So this is a famous type of force. It's got an inverse square law. This type of inverse square law, this logic of double the distance, 1/4 of the force, happens all the time for electric charge, for magnetism, and for gravitational problems. Those are the ones that we're going to work on. Now, so that's cool. And if we go again, we could even go, if we double it again, I guess. Well, yeah, let's not. I just want to have let's call that good. Let's see if there's anything else I want to say about this. That's basically it for getting some intuition here. All right. What if I wanted to get the force of 2 on 1?
Invert it.
What do you mean?
Take F1 on 2, just minus F1 on 2, or negative F1 on 2.
Yeah, so this is the easiest way to do it. F of 2 on 1 is equal to, by Newton's third law, negative F of 1 on 2. And so in your calculations, we spend a lot of time getting the first vector right. And then the second one, we could just say, hey, all I got to do is just use Newton's third law. Now, whoops, let's go to here. You might think, what are some applications of this stuff? So in this case, let's start with this one. We could actually have this mass be moving, right? And so you could give the rocks some momentum. Now, in this case, look at this mass. Rock 1 has got an enormous mass. As a result, I'm going to ignore the motion of the really big mass. This is times 10 to the 10th versus this one, which is only 200. So this is what, 80 billion versus 200. The bigger object is going to basically sit still. And so now when I run this problem, let's take a look at it. It's moving. So we see I changed the arrow color when it hits saturation level. Do you think acceleration is constant? What's your gut tell you? I can clearly see this thing is accelerating. Whoops.
The force is increasing as it gets closer, so the acceleration is not constant.
So should we be using energy? Should we be using kinematics to analyze this motion?
Nope.
No, there is an exception. We can use kinematics in the code down here, right? Isn't this basic constant acceleration kinematics? Yes. However, what we're doing is we're splitting this thing up into small enough step sizes such that it doesn't matter that much. All right. And so it's approximately constant for one time step, but you can't just do kinematics from the initial position to the final position. So in this case, eventually we'll start to see some separation there. There we go. You wouldn't want to do kinematics for, oops, let me get a marker here. You wouldn't want to compare this point to that point using kinematics. But because this is sliced up so thin, you could compare any two adjacent points using kinematics, and it would be approximately valid. All right. So in that sense, just watch out for using kinematics. If you're coding, it's okay because of the small time step. All right. I'm going to pause for a second. This is just to give you a feeling for how this stuff works. Think about this. I can't show you an object that has a mass of 80 billion kilograms in the lab and have another one. And like, it's impossible for us to actually touch and hold these. I can't put the moon in the lab and show you as a demo. So these forces are so small, we cannot really visualize them unless we do simulations. So in this sense, this is the first part of the class where maybe we could have gotten by without simulations before, but now you kind of have to do simulations to do anything realistic and visualize it. Okay. You can't just make a video of this, right? You can't video the Earth going around the sun. That would be a really long, boring video, 1 year long. All right. So, all right. Questions before we look at the workbook and grind through some math. All right. That was to motivate why we might care about this and how to work on it. So let's go into here. I think I said it was page 117. Let me get there. All right. So there's the definitions in case we need them. And let me get this door shut here. All right, so I've kind of alluded to most of this stuff already, but there's your definitions if you need it. We're going to learn where this definition came from, but it turns out this is gravitational potential energy. Can you do me a favor right now? I want you to underline this statement right here with a pair. It turns out gravitational potential energy is not stored in a single object, so to speak. It's actually shared between two objects. So if you have two different masses, they share that potential energy. Now, on an object like the Earth, and then a box, we have already discussed ad nauseum. But if this little box up here has a tiny mass compared to the Earth, we know almost all of the motion is associated with the box, not the Earth. That said, technically, there's going to be a force on the Earth upwards of equal size corresponding to Newton's third law. So there's a gravitational effect down of size mg on the box. There's an upwards effect mg on the Earth. If you wanted to calculate this, notice in this force equation, G m mass of the Earth over r squared. That's the magnitude, right? Well, G times the mass of the Earth over the distance from the Earth's center. So again, the radius here in these problems is the radius from the center of each object. That happens to be 9.8. So if you're wondering where little g comes from, it's from these terms right here. Big G times the mass of the Earth over r squared. Okay. In any event, when you talk about potential energy, just like the force acts on both objects, the energy is shared between both. Again, with something as large as the Earth, we don't really notice the Earth moving up to meet the box, but it is sharing that energy. So just be aware of that. Let me check the chat here. Yeah, little g. Yeah, so he's working on that, but his raps all involve physics, so it's not very popular. Yeah. Okay. So sorry, it takes me a while to get caught up on the chat. Okay, so there's that. Look at this. Underline it again. I've said it twice. Underline it again. All right. Let's start with this problem here. Okay. During a solar eclipse, the Earth, Sun, and Moon are aligned as shown in the figure. So not to scale. Obviously, the Sun is a lot farther away than that. All right. So in this case, let's say we want to get the magnitude of the gravitational force exerted by the Sun on the Earth. All right. So And I've got this written here. Oh, let me check here. Oh, I just caught up. All right. So I know this seems silly. Please get out your calculator now and actually punch in the numbers with me. That is the point of this problem, right? I want to make sure we find out what trouble you have punching things in. Let me get this here. There we go. So let's make sure you can punch this stuff in your calculator correctly. In particular, a lot of you probably don't use the EE button, but you should. So let's make sure we'll leave that up there just in case I forget. So I want the gravitational force of the sun on Earth. And we're going to do these faster in the future, but let's get one of these done really detailed. Oh, there's a rainbow unicorn if you need that. Okay. All right. Let's see. So I'm just getting the measurements here, right? So I want G times mass of the sun, mass of the Earth. Obviously, the order in which you do the masses doesn't matter. Now, you could do this in any way. Oh, we're just getting the magnitude. So if we're getting the magnitude, I'll show you a trick. If we're getting the magnitude of the force, I can erase the vector, I can erase the r hat, and I'm good to go. So notice there's a big difference between calculating the magnitude of the force, which we don't have to worry about the r hat vector at all, and getting the actual, So in this case, 6.67 times 10 to the minus 11 Newton kilograms squared. Wait, Newton meters squared per kilogram squared. Mass of the sun, 1.99. Geez, these masses are astronomical. 6 times 10 to the 24. For the Earth. Now, what radius are we going to need here? What do I put in the basement? What number?
1.50 times 10 to the 11 squared.
Yep. So notice this is the issue that you're sometimes going to face is you got a lot of powers of 10. And there's meters on that, right? We've got to have powers of 10 and squared and a lot of scientific notation. So just in case it's been a while since chapter 1, let's make sure we still have got that down. And so when I'm doing this one, right, what you could do is you could use the EE button. So 6.67 EE. EE negative 11. Not minus 11, negative 11. All that's said. So that's just your review. And then you get the rest of it. So 1.99 EE 30 times 5.97 EE 24 divided by, watch your parens, or you don't have to have them for this one because it does order of operations, right? But you could also just divide by 1.5 EE 11 and then divide by the other 1.5 EE 11, or there's parentheses any number of ways. So what did I get? 3.52 times 10 to the 22. And then what are the units?
Newtons.
Let's verify that works out. So I got a meter squared, 1, 2, cancels these 2 because it's squared. Kilogram squared, 1, 2, yep, newtons. Nothing too crazy. Just make sure you're fast with scientific notation and using a calculator. That was all. Everybody cool with that? All right. So I'm going to share screen really quick. So that was just to kind of get you used to punching in the numbers. Now I'm going to get the gravitational force exerted by the moon on the Earth. What's your gut tell you? Which one should be bigger?
The sun on the earth.
Yeah, let's go take a look. You can see it in the last part. So look at that numbers, right? So in this case, that is the when I see, we'll get to the energy ones in a second. Here's the deal. The moon is about 400 times closer, but it's got such a small mass. All right. It's 200 times less force. Now, the issue here is, well, we'll come back to that at the end. So, all right. So because the moon is so small compared to the sun, that 10 to the 30, right? Look at that. Isn't that crazy? All right. So, all right. Now let's get the potential energy associated with the Earth and the sun. When we do that one, look at the formula. There's a minus sign. So punch that in really quick. Punch in the numbers and make sure you get it. Just double check. It's negative 6.67 E negative 11 times the mass of the sun, which is 1.99 E negative, E positive 30 times 5.97 EE 24, right? Yep. And then divide by just one of them, right? So this is the thing, is people get in the habit of using R squared all the time, but the energy only has one R in the bottom. I'll explain why later. So divide that by 1.5 E negative, E positive 11. So I got negative 5.28 times 10 to the 33. Let's see if that's what I got before. Oh yeah. Okay. So depending on how you round and how many extra figures you keep, that's fine. So maybe this should be an 8, but I apologize if I did a different rounding this time than last time. Notice the minus sign has to be there. So on a final exam, some of you might get a question about force. Some of you might get a question about energy. It's important that you actually remember which one has the minus sign here. Now, if I look at this, help me here. If I add the two results, we do not have the total potential energy stored in the system. Okay, so there's energy associated with the Earth and the sun. There's energy associated with the Earth and the moon. Why doesn't it give me the total potential energy of the Earth?
Because we still need the potential energy between the moon and the sun.
Exactly. So this also will contribute some potential energy. So notice with 3 masses, there's going to be U associated with the first 2, plus U associated with the first and the third. And now I've paired up 1 with every other possibility. So I go on and I do the next one. U2, well, I've already paired it up with 1, so I don't want to double count that. The only other option is there. So I see that there are 3 ways to choose pairs from a set of 3. All right. There are, what is it? Yeah, anyways, let's leave it at that. Now, whoops. It turns out the sun exerts a much larger force on the Earth, yet the moon has a greater influence of the tides. Does anybody happen to know why?
Is it because the moon's closer?
It is closer, but it's still a much smaller force.
True.
How does being closer help? Yeah.
Aren't there like tidal forces or something?
Yeah, so it's actually, the tides are a little bit complex, and we'll go into this at the end, but I just wanted to point this out. 1 over r squared looks like this. This is the function 1 over r squared. Whoops. So again, I'm just plotting here. This would be distance, and this would be the gravitational force. Now, the idea here is, because the moon is very close to the Earth, the amount of gravitational force from the moon will be changing rapidly from one spot on the planet to another. For example, the North Pole and the South Pole compared to the equator. So again, because the moon is very close to the Earth, relatively speaking, there's more change in the force over the size scale of the planet. Whereas for the sun, when you're very far away, the force between the front and the back side of the planet are almost identical in size. So even though the force from the sun is much larger, it doesn't change as rapidly because you're so much farther away percentage-wise. Enough on that for now. But did you have a question about that, or did that kind of make sense? Or all right.
So it just
Oh, go
relates
ahead.
on the rate of change.
Yeah,
It's
exactly.
much greater. Okay.
It's the df dx, so to speak.
Okay.
So the rate of change in the force as you move to different spots on the planet, because the magnitude of the moon force on the different parts of water on the Earth changes dramatically. That's what causes the tidal bulges much more so than the sun's force. Yeah. If you're into that, if you're into tides, I'm just going to mention this since we're alluding to it now, and then maybe I won't come back to it later. If you really care, page 125 goes in depth on the tides and tells you some good web resources. And I think NOAA, NOAA, Tides Education is pretty good. So it's just not simple. There's some good videos out there too, and maybe I'll find one and send them to you. But yeah, so there you go. Page 125 if you're passionate about the tides. All right. Next. Okay, so that's just kind of a warm up on the numbers. 13.2. I don't want to spend a lot of time on this one, but there's one key thing that happens in a huge number of these problems. The gravitational force problems that we are going to talk about usually talk about the center to center distance. So in all the problems that we've been talking about now, I didn't really emphasize this, but the radius that we are going to use is between the centers of the objects. Okay, so the radius that you need to use is from the two objects' centers of mass. All right, so sometimes that's called the center to center distance. However, for airplanes flying above the Earth, they always talk about altitude. What about satellites, right? We talk about their altitude of the orbit. So very, very often what we do is we talk about the radius of the astronomical body, the planet or the moon, and then we talk about the altitude above the surface. So instead of using r, we say little r is equal to the radius of the planet itself plus the altitude. Now, when you do this, all it does is it changes the bottom of the equation to a slightly more annoying form. But this is very common in many books, so nothing crazy there. Now, notice the following. This result is the same as F equals mg if everything except small m is used to be little g. All right? So if you want, you could actually see how little g changes. And I did this for you. So I just plugged in a mass that was 1 kilogram. And when we do this one, hopefully we can go look at this. Solutions here. Oops. Watch these units. So this is a good one to actually plot. Notice we've got kilometers and megajoules here. So do actually pay attention to this one. Now notice the following. If we look at this chart at sea level, G is 9.8. If you go up 100 kilometers above the surface, 60 miles above the Earth, it's still approximately 9.8. It's not a constant, but it's pretty damn close. Certainly for most human beings, we're rarely going to get above about 10 kilometers above the ground, right? So you might go flying in a plane. Maybe you'd be 35,000 feet, right? So divide that by 3, that's maybe 10 kilometers-ish. So on that scale, the G that we have been using all the time is approximately constant. However, when you get really far away, so at 20,000 kilometers above the Earth's surface, there is a much smaller G force up there. So again, I used a 1 kilogram mass. So if I divide this column of F by 1, I should get G. So that's why I did it this way. I used a 1 kilogram mass. That way this column, the middle column, would correspond to G. As you go into orbit, you are not weightless. You feel weightless. You perceive the feeling of weightlessness. If you jump off a building, you feel weightless until you hit the ground. That doesn't mean you are weightless. Weight is the force. That force gets weaker as you go higher and higher into the atmosphere. And eventually you could argue it becomes negligible for heights above, say, 30 or 50,000 kilometers, but it's you're not weightless, right? You feel weightless. All right. All right. Any questions about that? All right. Let's go back into here. Please take the time to actually do this problem and just make the plots. I know you don't do it very often, but there's just some things with units and stuff that should hopefully make you faster on test A, right? You just want to have this stuff be automatic. All right. Here's another one. Let's look at this problem and just kind of play with it a bit. And let me make this bigger. So a typical thing might be to have a satellite with some mass in orbit at some altitude h around a planet. If we assume the mass of the planet is much, much bigger than the mass of the satellite, we could assume the planet is stationary and use the center of the planet as our coordinate system. So over here. So I'm just going to make this bigger so I could draw right on here. Sorry. And let's maybe even make it one more. All right, so here's our picture. What is one force acting on that mass? So I'm going to do an FBD over here. What's one force that's acting on that mass as it tries to orbit? What's one force acting on the satellite as it tries to orbit the planet?
Gravity.
Gravity. So we can't just use mg anymore. So we're going to use g m m over capital R plus h quantity squared. All right. That is the force magnitude. And that's going to point down, right? That's the force due to gravity. I'm just drawing an FBD for this at the instant shown. So that's the force due to gravity magnitude. The direction is in the direction shown. What are the other forces acting on that object?
Is that the only one?
It is. So this is actually one of the easier FBDs we ever do, but it's very disconcerting for students who are used to having 5, 6 forces at angles. This is it. Which way is this thing accelerating if it's moving at constant speed?
AC. Towards
AC. All right. And what is AC equal to? What's the equation for AC for FBD usually?
What is it? V squared over R or something like that?
V squared over R. And in this case, what should I write instead of little r?
Oh, R plus H.
Yep. Big R plus H. So notice you have to pay attention to capitalization a lot in this chapter, whereas we haven't had to a lot in the past. That's it. All right, we've got this thing. So now if I wanted to, I could get the equation. Notice that one of the radii is going to drop out. So we get, let's write the force equation. So I get G M M over capital R plus H quantity squared. That's the forces. All that should equal what?
Now would it be little m plus big M AC?
That's what I was wondering. It turns out which object is feeling this force. For which object did I draw an FBD?
For the satellite.
So
would
what
you
mass
just
should I use?
little m?
Yes, and that was what I wanted to point out. In the FBD, now if we were doing potential energy, then it would be some combo of the mass. You know what I'm saying?
Right.
All right, so watch out for that. And now that we've seen this trick, now you won't have any trouble with that. Now, in this case, I'm just going to put parentheses around this just so I could see that this cancels one of those. This is canceled by that mass. And notice we get the V. You could solve for V. Once you get the velocity, you've got it. Do you agree we could get the kinetic energy?
Yeah.
That's just 1/2 mv squared. Why is it okay to use 1/2 mv squared even though it's rotating? Shouldn't I have to use 1/2 I omega squared instead?
Does it have to do with it being a point mass?
Yes, if this is a point particle, I of the point particle would just be mr squared. And we know that r squared omega squared is equal to v, right? And here, to be clear, little r is equal to capital R plus h. So you could use either. And it turns out, why not just get right to the heart of the matter and skip right to this one? So anytime the particle in circular motion is a point particle, you could just say 1/2 mv squared. If it's an extended object like a ruler or something, then you have to use I omega squared or a hockey puck or something weird. All right. You could also get the potential energy. That would be negative G M1 M2 all over R, capital R plus H. Now, at first, you might not notice this. Which energy do you think is larger in size? Do you think it is the kinetic energy has a bigger number, or do you think the potential energy has a bigger number, albeit negative? But basically, if I took the absolute value of the kinetic energy and compared it to the absolute value of the potential energy, which one do you think would be larger? I'll give you a hint. Look at this equation. Before I cancel the m's, can you tell what the kinetic energy is going to be?
Is it half that?
Yeah.
No.
If you plug in all the numbers there, right? If you don't cancel this m and you multiply each side by 1/2, you've got the kinetic energy. Do you see that? So what is the total energy? Positive or negative? If you add up the total energy,
So it's negative 1/2.
it's negative. Now, at first, this may seem disturbing. I don't want you to get freaked out by this. This is actually a useful and standard trick. The idea here is for orbiting objects, anytime the total energy is negative, the orbit is trapped and the particle cannot escape. Now, maybe you took chemistry. Maybe you know about the energy levels are minus 13.606 eV divided by n squared. So you've seen this in chemistry where the energy levels they're closely spaced. And then as you get down here, the energy levels are negative. Now, what does this mean? If you've seen this in chemistry, great. If you haven't, don't worry. Let's say these are energy level 1, energy level 2, etc. And then they start to get so close together, I can't label them all. The idea is the energy of any one level is negative, but we don't care about the size of the number itself. What we care about is changes in energy, delta E's. Remember, I said only changes in energy are physically meaningful from a potential energy standpoint. So the trick here is if you add energy, it becomes less negative. That's like saying it started out at 0 and became more positive. So potential energies being negative is not a problem. In fact, if we look at our equation, GMM over R squared, and it's over R, excuse me, I'm doing the potential energy formula for 2-point masses. What value of R gives you 0 potential energy? What value of R gives 0 potential energy?
Infinite?
Yes. And so the idea is the potential energy versus position looks like this. And so as you get farther and farther away from the planet, U goes to 0, it doesn't affect you anymore. So it actually makes sense in that standpoint to still use this equation. Now, changes in potential energy are still getting bigger as you go up. As you get away from the planet, you go to a higher radius, you become slightly less negative, you become more positive, your energy increased. So it's weird, but it works. And it allows us to not have to change all the definitions we have in physics just to make you feel better. So
is it kind of like when you set H, right? When you set H on the energy equation, so it's basically saying like the highest point is 0 and then everything below is negative.
Exactly. And so, yeah, now we're setting the top of the problem to 0. So infinitely far away, we'd say, okay, this value is essentially U equals 0. And then every other point is negative. And as you get closer to the planet, you get more and more negative. This would be like negative 7,000 or something. This might be negative 6,000, et cetera. You got it?
Yeah.
Yep, absolutely. So that's exactly what it is. Now, you might be saying, this makes me feel uncomfortable because I like to use MGH, right? So I just want to point out, this is something you might not expect right away. Where is it? Oh, here it is. Question 13.12 talks about this, and maybe 13.11. So I'm going to allude to this. The definition of potential energy was minus the work, right? And I should be careful. The change in potential energy was minus the work, which is minus the integral of F dot ds. So this was from chapter 7. All right. From chapter 7, we actually still do use this, and we're going to use it again a couple of times in the next class. So there is our equation. Now, as you move outwards, ds is going to be a small change in the radius radially outwards. If you do this, you get this equation here. So if you do all the work, and if you set U equal to 0 when R final is equal to infinity, we get this result. So that's where the result came from. If you are passionate about understanding where the result came from, 13.11 is the problem for you. Just read it and write it down, and you'll have it forever. We're going to use this same trick in Physics 163. Now, in chapter 8, this is where it looks very weird. You're like, dude, in chapter 8, you said it was MGH all the time. Now you're telling me it's this crazy equation. How are these the same? It turns out if you do a Taylor series approximation, they give the same Taylor series. What? Now, rather than doing Taylor series, I introduced this trick, binomial expansion. So if you want to see why these things are the same, you should do this problem and learn about that. We'll try to come back if I have time and I'll just show it to you. But it does actually work out to give you the same change when H is close to 0. When you're close to the surface of the Earth, this energy equation and this energy equation give the same delta U's. Again, the new energy equation and the old energy equation for gravitational potential energy will give identical results for changes in potential energy, which is the only thing that is physically meaningful, when the two heights involved are much less than the radius of the planet itself. All right. Now, you may say, why should I care about this? This trick of this binomial expansion, if you go through the work and do it, is used all the time by physicists. So if you are a physics major, you have to do this problem, right? I'm not going to put it on the test. It's not going to be on the final. But if you don't do this, you're going to feel like an idiot when you transfer. That's why I'm telling you to do this one. So you really have to understand binomial expansions. We use them on occasion. Physicists use them regularly in upper division classes. Engineers will use them to take ugly formulas like this and make them simple looking like that. Isn't this second form just a lot prettier? Look at these two equations down here. This one sucks. This one's easy. It's linear. You could take an ugly function like this and make it linear, or you take an ugly function like that and make it linear. This is a useful trick to converting ugly equations into linear ones. All right. Enough on that. I feel like I'm all over the place, but
I had a question on that.
Yeah, go for it.
Do you lose accuracy when you do that, or is it like
Yes.
negligible?
Well, so the accuracy depends on how many terms you keep in the Taylor series.
Oh, okay.
So for now, what you usually do is, as long as the thing you are expanding about is very small, like say 100 times smaller. You know what, Christian? I could go through this in office hours with you right afterwards, but it suffices to say, let's say you make let's say H is 1% of the Earth's radius. Then you could expect the expansion to be accurate at least to 1%. Is that good?
Yeah, that's good for right now.
Yeah. And I could show you and we'll walk you through it right after class. All right. I just don't want to beat people up for something that's not on the final, even though it's really, really important to physicists. All right. Engineers, probably some too. All right. Oh, let me show you something here. So let's go back and look at one last code really quick. Let's run this one. I don't remember what I did. Okay, so here we have a particle going around the planet. And so if you're curious, all I did this, you're going to do this week in lab, but this would be a circular orbit, right? And so if you look at this one, it's not perfectly circular. You might not know what I'm plotting here, but this is supposed to be radius versus time. And so notice the radius is actually changing. It's on average about 4.7. So this is not a perfectly circular orbit. But if you get just the right size speed, this should be a circular orbit. But what's going to happen if we jack up the speed or change the speed somehow? Let's say we make this 240. Whoops. And hopefully, let me check and make sure. Yeah. So if I make this faster, what type of orbit shape do you think we will get? It's an ellipse with the Earth at one of the focal points or the central body. Now, again, the center mass is not moving because it's so much bigger. Now, look at the radius changing now. It's varying between about 5 and 10.5. And so here, if you get just the right velocity, the radius will actually be constant and you'll get a circular path. But Yeah, depending which way. So anyways, if you try to do forces on this one, this is one of the advantages of coding. In coding, look, we're still doing exactly the same force calculation. And then I'm animating this thing just the same way as always. First, I compute the force. Well, okay. First, I get the current positions. I use that to get the current value of force. Then I update the momentums here. All right. And then I update the positions and you just plot it. It's like, yeah, that's cool. So it's actually so easy to do elliptical orbits in a code, whereas it's extremely difficult to do them on paper and pencil in comparison. If you wanted to do this same problem on paper and pencil, where is that one? Let me see if I could find it. Sorry, I've got it here somewhere. Right here. 13.10. It's just tedious and unfun. All right. So you could do it, but you have to do conservation of angular momentum. You have to do conservation of energy. It's a nasty problem. The radius of circular motion is changing. So, right, as you move around, the radii, the radius of curvature of these paths is not just the easy thing that you think. For example, here, the radius of curvature here, I forget what it is, but I think it's actually bigger than or smaller than r. It's not just 2r or something. And here, the radius of curvature is not, it's not necessarily centered at the middle of the screen or at the focal points. It's extremely complicated and tedious compared to just coding things. All right, I'm going to pause for a second here. Questions right now. I hope I'm not losing you. I'm trying to give you some exciting feelings about this and show you how this might be useful. How about this one?
Remember,
oh, go ahead.
This is totally off topic. We're not really off topic, but I remember watching a video where they were trying to when they were first discovering planets around suns, around stars, and they were using the fact that the star still circles around the center of mass, but varies so slightly, to detect whether there's a planet orbiting it. And I thought, I was like, after this, what you were saying, I was like, man, how sophisticated does their equipment must be to be able to detect something that massive still spinning around the center of mass, you know?
Yeah. Let me give you an example. So you could do all the math for this. Actually, it's not that crazy. Hold on. I've got it in here, Esteban. This is what he's talking about. Let's say you have two objects and one of the masses is not infinitely bigger than the other one. What happens is both of the objects tend to orbit the center of mass. So the big object will rotate about that circle size, and the smaller object will rotate like this. And you'll see these two circling around. And what he's saying is astronomers were able to tell the difference between the star being in this position and that position. And they could say, well, I could tell the diameter of the star's oscillation must be this. And from that, it relates to the masses of the objects involved. Absolutely. And I think that's what you're talking about, right, Esteban?
Yeah, I just think that's crazy.
It is crazy. By the way, it's also not on the final exam. But if you want to learn about it, or if you've ever heard of reduced mass in your chemistry class, and we're going, what the heck? Where does this come from? It comes from do this problem. And now I have discovered in my experience, trying to use v squared over r for this problem is annoying because the two objects end up with the same omega. So it's easier to do this problem by thinking about AC as r omega squared. So if you physics majors, you're going to see reduced mass later. So just keep this in mind and look at it in the summertime or something, okay? With all your free time, do more physics. All right. Yeah, that's a cool one. Other questions? That's a good comment. And that's how they did that, Esteban. Yeah.
When I first learned that, it didn't make any sense how they orbited something, but now that I know center of mass, that makes complete sense. So that's cool.
Yes. So where's the center of mass of the Earth-Moon system? Does anybody know?
It's inside the Earth, but it's a little more.
Yeah. So this is another contributing factor to the tides, right? So if I remember correctly, now I'm not an expert on the tides. So if you want to learn about tides, go to that resource I mentioned because they are the expert. All right. But the idea here is here's the Earth, here's the moon, and the center of mass of the Earth moon system is actually just slightly off center. I think it's 1/3 or 2/3 of the way out. I forget what. It's like 1,000 miles from the actual physical center. And so as a result, the Earth is orbiting like this about its center of mass, whereas the moon is orbiting like this about that. And you could imagine this makes the motion, the Earth, it's approximately in the Earth's center. So if you were just doing a first calculation, you'd say, assume it's right at the center, right? It's only off by 1,000 miles out of 200,000 or something, or whatever it is. I forget. But yeah, if you had to get this exactly right, and the next level would be first calculate the center of mass position. And what's interesting is this reduced mass trick. What it allows you to do is say, hey, this thing actually orbits about a different radius, but instead what we're going to do is we're going to say this thing's fixed in place, and we'll give this a different mass in such a way that it's mathematically equivalent to orbiting this one as it's fixed. And so it takes a complicated problem where it's orbiting center mass and blah, 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 and turns it into a simple one where the central object is fixed, and this one has an effective mass of some other smaller size.
It's kind of like parallel axis theory.
Yeah, in a way, yeah. And I don't know exactly how the analogy would work out. So obviously there are very different types of problems, but something kind of like that. Yeah, sure. Cool. So yeah, very good. Other questions? Isn't this stuff interesting, kind of? I don't know. It feels a little different, and yet the math is pretty straightforward. Let's get back into it. All right. And I'm keeping an eye on the time because let's see, that rocket launch is in a little bit. So I was hoping to take our break right near the rocket launch just in case. All right. Okay. Sorry if it's drudgery till then. Interrupt me at any time and ask questions. Okay. Let me see here. There's a question I think we should look at, and I'm trying to remember which it is. Let's do 13.5 now, okay? Okay, so we've got 3 masses sitting on a table. So 1, 2, and 3 kilograms respectively. So mass 1 is 1, mass 3 is 3, etc. The center to center distance is 30 centimeters. 1 and 3 is 40 centimeters. Okay. If you want, these are the colors I used. So I talked about green for the force of 1 on 3 and red for the force of 2 on 3. Sorry, red, green, colorblind. I should have updated that. I have not yet. But it's labeled as well. So which mass is going to exert more force on M3? What's your gut? So I want to find out the forces acting on this mass. That's my goal. And my question is, which object, 1 or 2, should exert more force on object 3 due to this gravitational force? What do you think?
Mass 1.
And what's your reasoning?
That R squared.
It's closer. What do you think about object 2? What would be the reasoning for thinking that it's got a larger force?
More mass.
Yeah. Now, in this problem, it's not obvious. Do you agree?
Mm-hmm.
It's kind of, now I would think the closer distance might dominate because it's squared. However, the distance is only 20%. It's not obvious. So would you give me this? Would you agree it's reasonable to think these two forces might be about the same size?
Yes.
Yeah. And so here, that is the logic we could use to check this problem. I don't know exactly which one should be bigger. I might think M1 because it's a little closer. I might think M2 because it's a little bigger, but they're probably about the same size. That's all I wanted to point out. What direction is the force of 1 on 3? What direction is the force for 1 on 3? Here's object 1. It's going to exert a gravitational force on object 3. Which direction?
Up.
Straight up, J hat. Force of 1 on 3. Got it. Now, what direction is 2 exerting a force on 3?
Diagonally.
Yeah, somewhere right there, right? Now, we don't know which force is bigger. What direction should the net force be, if you had to guess?
Somewhere between the both arrows.
Somewhere between them. And that's the check you could use. Now, we could do the parallelogram rule, right? There should be another force up, and there should be another force out, right? Doing the tail to tip, tail to tip. I feel like I'm doing Christmas physics here. But we'd expect the net force should be somewhere in between there. Now, you might be saying, well, this seems kind of silly, but isn't that nice to kind of have a check on your answer? Let's say you had to type this in on Canvas and you got the X component to be twice as big as the Y component. I bet immediately you'd be like, oh, whoops, I flipped a minus sign somewhere, and go find it. So that's what this is good for. We can draw the pictures to get a quick feeling of which direction the net force on 3 should be. Nothing more than that. Is everybody okay with that? You could draw the arrows to get a feeling for it and figure out the approximate size of the relative forces and maybe the approximate direction, but don't put too much faith in it. Just kind of get a feeling to check your answer. Clearly, it should be more in the J hat than in the I hat for this problem. That is all you can really use that for. All right. So let's go in and take a look at the solution. And apologies if I'm going too fast here. 13.5, I think we're on. Oh, there's a cool one. 24-hour period happens at about, what is that? About 35,000 kilometers. You see that? That's cool. All right. I think it's this one. So here are two styles of doing the math. They both have pros and cons. Most students at this level significantly prefer style 1. Look what I did. First, I get the force magnitudes. Then I split them into components. How do I do that? On this one, notice I have to figure out the angle here. Well, I said cosine of theta is 30 over 50, which is 0.6. Notice I didn't get the angle. I got the cosine of the angle. Here, instead of getting the sine, or instead of getting theta, I got the sine of theta. So I could punch those numbers in, and notice I get the minus sign in the I hat, and I manually stick it in there, and then you just add them up, and then you get the magnitude. So I'm going to pause here. Is everybody okay with style 1? Take a minute to look through it. I'm going to give you 30 seconds to look at it here. Look at style 1. Ask me any questions you have on style 1, like where did you get what? Sorry about that. If I scroll down, I think you could actually see the result. Ooh, talk about foreshadowing. All right. Is everybody okay with style one? I'm going to assume so, unless you have questions. Interrupt me at any time. Anytime. Okay. Style two is something you might not be used to. Notice I actually got the R vectors or the R hats. So at here, we're doing the sines and cosines. Here, what I'm doing is I'm getting the R hats instead. And notice, how do you get R hat? It's write the R vector, then divide by the magnitude, right? So this was 30 centimeters in the I hat and negative 40 centimeters in the J hat. So notice you might be saying, wait, isn't it going the other way? Well, remember, this was object one, or wait, no, this was object two, and this was object three. So two towards three is positive in the I hat, negative in the J hat. By definition, the force uses a negative R23 hat. So that's where the minus sign comes in. Immediately, most students say, oh God, this is stupid, dude. I hate this way. And this is the better way. Well, I think you've seen that when we code it, this way is much better because it's full 3D from the get-go. So if you're doing three-dimensional problems, the style on the right is much better. If you're coding these things, the style on the right is much better. All right. Do notice that basically this 30 over 50, the sine and the cosine here is right here as well. 30 over 50, you get the cosine. So it's just a different way to get sine and cosine that works in 3 dimensions. This style over here only works in 2D. As soon as you get to civil engineering classes or the next level, right? It's like, well, everything's in 3D in the real world. This style will continue to work. That style will not. All right. Interrupt me at any time. Here's something that drives me nuts. Students sometimes will say, oh, I'll just take GMM over X squared for the I hat part and GMM over Y squared for the J hat part. The units work out. Everything looks pretty. It's just wrong. It doesn't work that way, right? You need the total distance in the basement and then split it into components. So again, first get the force magnitude using the total distance, not just the X component or the Y component, then split it into components separately. You'd be surprised how many times students write this. They get in a hurry on the final and they're like, oh, I'll just get the X component with X. Well, you did get the X component, but it's incorrect. And so you get the points off and it's just like, oh, you were so close. You knew almost all of it and just, yeah, it's just brutal. So, all right. Here's an interesting thing you might read about. The Earth exerts a gravitational magnitude of 30 newtons on mass 3, right? Because M3 was 3 kilograms, G is about 10. If you look at the size of this force, this is about 3 nanonewtons. So going back to the problem, the forces that these different spheres exert on each other, the force that goes this way is negligible compared to mg, which is going into the board. Mg is 30 newtons into the page. The normal force of this ball is 30 newtons coming out of the page. And then there's this tiny force of about 3 nanonewtons going this way, which is offset by a tiny frictional force going this way. And that's why the balls don't suddenly start moving towards each other. It's really easy to come up with 3 nanonewtons of friction to keep these things from sliding around on a table. If you ever go out to the club, right? This is strange to think about. You used to be able to go out to the club, but if you went out to the club, you could always feel attractive if you consider the gravitational force. It's just not attractive enough to do any good. But just keep that in mind. You know, if you need a self-esteem boost going out to the club, just use gravity. There, you're always attractive using gravity. All right. Questions? Dumb jokes. Any questions? That's basically the entire chapter. We've got to do some energy problems. Hey, that's right, man. That's what I got going for me, right? All right, so let's get back in there. Let's see. It's almost time for that launch. Let's go. Let's take a look at one more problem. This is a deceptive problem. Looks really easy, right? Everything is on the x-axis. So all the components are in the I-hat. I want to show you, even for problems that aren't 3D, sometimes using this R-hat style is very useful. So take a second to look at 13.6. You've got a big mass, capital M, a bigger mass, 2m. And then in this one, the trick in this problem is really just this. What is this radius right here? What's the radius for this one?
D plus X.
D plus X. Whereas for the other one, it's going to be D minus X, right? However, it gets complicated. What if X is sitting over here? What if X is sitting over here? What if it's over here? It gets very complicated trying to think about this if you use distances. Notice these are distances. So I argue it's a bad idea to write this kind of problem with distances. Let's show you how I did it using displacement vectors between them. What was that? So if we try to figure these all out, you could see there's different distances involved. And notice in this particular image, I put X. So here's the center. I said X is way out here now, right? Now, in this case, every different scenario could have a different way of writing this same problem. All right. However, if we go down to here, I think it's, here's the style I thought was, ended up being useful. What I did was I used this R-hat style of defining things. So I didn't have to keep doing absolute values in these weird ways. And this is probably more than you expected to get out of this problem. Basically, you can write the net force more rapidly if you do these R vectors here, rather than trying to do everything with distances. That's the point I was trying to get across here. Otherwise, you have to split things up into cases and do all this analysis. It's very complicated. All right. So the actual math for any one case is simple on that problem. But I just wanted to make you aware that sometimes it's useful to go to 3D vectors, even for a 1D problem. Let me show you something about that. One last thing, and then we'll take our break, I swear. Maybe. Come on. All right. Did I make the plots here? Something I learned when I was writing this book was you really don't understand what you are doing with these problems unless you can plot it. If you could plot it, you really understand it because you get the units right. You could tell, like, look at this function. It looks crazy. You can think about the signs of these forces, etc. And you could think, when should it be positive? When should it be negative? So I know a lot of you don't really care about this and making the plots, but this is a chapter where I discovered I really had a deep knowledge or gained a deep knowledge by making the plots. So you have to choose what you're going to do with the amount of time you have. All I could say is, if you have been plotting things all semester, it should be very quick to make plots. And I caught a lot of my own typos in this chapter by making the plots and finding out, wait, my equations don't make sense because it's upside down, that kind of thing. Moral of the story, make plots and you can learn from it. All right, so I think it's about time for that launch. So it says it's in about 5 minutes. So I have no idea if any of you are fortunate enough to be able to see that or not, but I'm going to try and go out in my backyard, see if I could hear it at least. And so let's start up here. Does anybody know if it's on schedule? Where do you go to check if it's on schedule? Does anybody know? I forget the name of that website. Let me just check really quick. Lompoc launch today. Launch schedule. Uh-oh. Looks like it says 4:46 p.m. I wonder if that's Eastern. Oh, that's Eastern Standard Time. Yeah. Delta 4 heavy. 140. Now it's scheduled for 1:47. It says it's go for launch. All right. So let's take a 10-minute break. So I know my clock's sometimes a little bit off. So I'm just going to come back in. Let's just take a 15-minute break today. All right. So let's come back at say 1:55 my time. So I guess that's 12 minutes. Okay. 12-minute break. Hopefully that's long enough to see the launch. 12 minutes. Any questions before I go? All right. All right. That was pretty cool, huh? If you got to see it, it was kind of neat looking. Whew. So maybe we should do one more problem and call it a day. So before I start back up, does anybody have any questions, or am I going too fast? Is there something I skipped over that you're kind of doing the highlights? Okay, let's get in there and get our fingers dirty again and actually do some of the problems. I know it's kind of lazy of me to just show you solutions. So let's try and make sure we do one together on the whiteboard and see the mechanics of it working out to see what technical details are going to hang up, what you'll get hung up on. All right. So I think you're starting to get a feeling for this chapter. Now let's get into the nitty gritty. Maybe today. All right, there it is. Let's try. What do I want to do here? Let's do 13.8. Okay, let's work out 13.8. And this is starting to look more like a final exam type question. All right. So 13.8, let's try and do it together. We've still got 15 minutes. Let's see if we can dial this in. And I'm just going to check in the solutions what colors I use, just so I can use the same colors. You don't have to do this, but did I do it? Oh, I didn't use colors. All right. This looks like a good one to do. All right. So we're trying to get the net gravitational force on mass four identical masses, square is side s. Let's assume the mass of each one is m. I didn't write that, but yeah. So I'm going to assume that each one of these is m and the spacing is s. Sorry, it's not a perfect square. All right, so we've got this square here, and I want force net on 4. So then what we could do, let's just say 1 is blue, 2 is green, and 3 is red. What was the first thing we did earlier before we did any calculations? Do you remember what I first tried to do to get a feeling for this problem?
Draw the force arrows.
Yeah. So if they're all equal masses, right, which force or forces is going to be the largest?
Shouldn't 1 and 3, or what's 2 and 3 be equal?
2 on 4 is going to be large and up this way. Three on 4 should be large and going this way, and it should be the same size. And then the last one would be force of 1 on 4. Now, so far, is that okay? That's just drawing it and getting a feeling for it. What direction is the net force? Sorry, this isn't exactly a square. Let me try and make this more square. What direction is the net force?
The direction of 1 on 4.
Yeah, exactly. So it's going to be up that way, right? All right. So we know the net force, this one should be 45 degrees. That's just a way to check our work. Once we know that, Does anybody see any shortcuts we could do? We could obviously get the net force of 3 on 4 and add that to the force of 2 on 4, and then add that to the force of 1 on 4 as full vectors, and we could code it and get it done. Sure. Or we could punch it into calculator. There's a faster way.
Well, couldn't you get the magnitude of 3 on 4 and then just times it by 2 and then add the magnitude of 1 on 4?
Now, careful. If I just multiply this magnitude by 2,
Or
that's still
the absolute value of that.
okay. But remember, one of them's in the I hat and one of them's in the J hat.
Oh, yeah, you're right.
So that's
right.
why we don't want to just double it. But do you
But what-
agree? Oh,
okay.
go ahead.
I was gonna say, but if they're both if we're just taking the magnitude and then using the R hat to
Mhm.
tell the direction, would
You
that
could
work?
then, yes, you could get the magnitude of it and then say this one negative I hat. You could use that same magnitude and say this one positive J hat. And then how do you get this one?
It would be 45-degree angle.
Just, yeah. And it's a different radius and you could work it out. How about this? What if I just said, let's get the X component of this particular case? Shouldn't that be minus the magnitude of F3 on 4, right? Minus, because it's force 3 on 4 in the negative I hat, plus F1 on 4 X. Just get the X component of this other one. And remember, this one we expect to be negative. So they would both be negative. So what you could do in this problem is say, look, I know it's 45 degrees. I could actually just get this one and this one, then just get the X component of that one, take the X component of the blue arrow, add it to the red arrow, and then I'd say, well, by symmetry, I know the Y component is exactly the same, and I got it. That's one way to do it. Here's another crazy way you could do this. Even though this seems a little bit nuts, what you could do is even do this. You could say, you know what? I got a square here. I'm going to make this the x-axis and this the y-axis. You could rotate the coordinate system, and then the blue one lines up on the page. And then you could get just the x component of this one, which happens to equal the y component of this one, right? Or whatever. So basically, you could split these vectors up and do components like this. These are the three main ways to do the problem. Number one is don't think, just add up the vectors for each and get it over with. That's a great method. Number two is be a little bit clever, realize I could just get this magnitude and that's the same as that other magnitude, etc. And then the final weirdest way is to rotate the coordinate system and split up the vectors on that new coordinate system. All right. That said, maybe let's start by just getting this method here. All right. So you could do it this way, and that's a cool way to do it, but it's 6 of one, half a dozen of the other. Force 3 on 4. When we do this one, that's going to be G M M all over S squared. I've already accounted for the negative I hat. This one is going to be G M M all over what distance? What's the distance in this one?
Square root of 2 S.
Square root of 2s. And then I've got to square it. And then I need to manually stick in the minus sign here and a cosine. Well, let's just do it this way. We'll say it's minus cosine 45. And the minus sign means to the left. So notice the picture is helping me draw this out. Notice how many minus sign errors you have to keep track of here, right? And avoid. You have to pay attention to minus signs here all the time. If you're doing this in coding, you don't. And it's easier in that sense. So there's strengths and weaknesses of having to use a code here, or using the R hat vector. If you do the R hat vector, you're not constantly having to think about these minus signs relative to your picture. Because we are so good at thinking about minus signs relative to our picture, because we've been doing it for 13 weeks straight, it's not so bad. All right. Now notice here, I get a g m squared over s squared in both terms. That's going to factor out g m squared over s squared times -1 minus cosine 45 over 2, because I square the root 2. Whoops. Which cosine 45 is root 2 over 2. So you get some weird number. This would be the force on 4 in the x direction. So there's an implied I hat here. Right? We're not actually drawing the vector in the I hat, but we know it's there. Questions on that?
So when doing the j hat, this x component is negative, right? So when doing the
Right.
j hat, we would have to just make it positive.
Exactly. But you don't have to redo all the work.
Mm-hmm.
So that's the advantage of drawing the picture and thinking about it. Because you're like, oh, I could kind of see these two should be the same. Those two should be the same. All right, got it. Cool?
Cool.
All right. So let's go take a look at the question and see what we did. Okay, so that was getting the net force. How about the net potential energy, or the potential energy? If I wanted to get the potential energy, what should I do? Give me a second. Okay. So last problem, we were figuring out the force on 4. We didn't quite finish it, but we found the x component and said from that you could get the y component as well. Got it. If I want the net gravitational potential energy, I need to figure out how many pairs there are, right? Don't overthink it. Start with object 1. This is my recommendation. What is one mass that you could pair up with object 1? 2. What's another one? 3. What's another one? 4. That's every possible way 1 could be paired up. Now I keep going. What's every possible way you could pair up 2? 2 is with 1, already done it. But I haven't done those ones. And then I keep going. I go to the next mass. 3. Well, I've already done 1 with 3. I've already done 2 with 3. The only one left, I haven't done 4 with 3. That's it. But wait, 4 has already been used with every single other one. I'm done. Now, if you aren't familiar with how to do this, you could actually find these. Maybe you know the combinations. If you say 4, choose 2, that's equal to 6. There's 6 possible ways to pair up. If you know Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you know Pascal's triangle, right, this is the number of ways you could choose 2 things. So if you had 18, you just write out Pascal's triangle to 18, or you do n choose 2, whatever. If you're interested in learning these math tricks, that's great. But essentially, we're basically going to restrict ourselves to either 2-point masses, 3-point masses, or 4. So if you have 2-point masses, there's only 1 way to pair them up. 3-point masses, there's only 2 ways to pair them up. 4-point masses, there's actually 6 ways to pair them up. Wait, what did I just say on 3? 3-point masses, 3 ways to pair them up. 4-point masses, 6 ways to pair them up. All right, sorry if I misspoke. All right. Once you have this written out, the math is straightforward. You get the distance between each one, and you recognize that in here, some of these are going to be the same. Let's look at U12. How many of these are going to have the same size as U12? Is U1, whoops. I wrote 2 number 4s. Was this a number 3? I think it was number 3. Yes. Let me double check. Sorry about that.
Yeah, it is.
Okay, thanks. Sorry about that. All right. Is U13 going to have the same size as U12? Remember, the equation is G M1 M2 over R with a negative sign. Let me get that negative out front. The energy equation is negative G M1, I'll call it MI MJ over R IJ, the distance between the R, the ith, and the jth.
So basically, they're all going to have the same potential energy except for 1 and 4 and 3 and 2.
Yep. So you could actually get this potential energy very quickly by saying 4 times this one plus 2 times that one, right? And it looks bad at first, but you'll see that a lot of problems have these symmetries in them where you can reduce the amount of work by being clever and thinking, oh, which thing should be the same size? That is the moral of these last 2 problems that we've done. If you look at a problem that's initially horrible, you can use symmetry to reduce the amount of calculations dramatically. Look at the problem and think, should the I-hats cancel here or not? Let me give you another example on the way out. One more. Let me see, where is it? No. Where is that one? Maybe it's after this page. Sorry. One last one. There. Look at this one. Potential energy. There's going to be 3 terms. If I want the net gravitational force on the middle mass, what direction is the net gravitational force on the middle mass?
Towards the left?
Yeah. So which component of the net gravitational force do we not need to worry about?
The Y component?
Exactly. So in this problem, this is what, 13.14? In 13.14, we've got a problem with a big mass here, a big mass here, and they're the same size. And you've got a little mass here. We'll call this little m. So I know, whoops, let me label it on the outside. Sorry about that. I know this upper one is going to pull it that way. The lower one is going to pull it this way. And because of the symmetry in this situation, sorry if it's not perfectly drawn, I expect that this component should equal that component, right? And I expect that the upwards component from the top one should cancel the downwards component from the bottom one. So here, the net force on M equals twice the force of 1 on M in the x direction in the negative I hat, so to speak. Now you could debate whether we want to include the minus here or in there, but something like that. So if you say, well, the force in the I hat is negative and I'm going to include it here, whatever. But Does that kind of make some sense? We're trying to save time by saying, look, get the force of this one, get the X component of that one, then just double it. Now, when we do this, I know this sounds a little bit crazy. I know we're over time, but let me just show this solution really quick, just to show you why you might like this other style. Notice you could do this one actually pretty easily if you use the R vectors and R hats rather than trying to do sine and cosine. So we see another advantage of learning the R hat method. If you're doing problems algebraically, it's easier. And I guess that's class. I'm going to see if I happen to have this simulation right here. If I do, great. If not, my bad. Let me see if I've got it here. Let's see, gravity, one moving mass. Oh, I don't see it right off the top of my head here, but you could actually run this one with different gravitational forces and you could see it work. So that's what we'll do in lab this week is you can actually add in the third mass and run this same problem and see. The weird thing is it'll oscillate back and forth. Think about this. If it starts from rest over here, it's pulled towards the center. What's the gravitational force on it right at the center? If you're right at the center here, up and down cancel, there's no force on it. Then when you go this way, the force is that direction. So this thing should oscillate back and forth, right? And it actually acts just like a mass on a spring. Very cool. That's it. Let's